You've done a independent variable distance from something, up a tree, from a river, and then you've done 5 trials, taken 5 trials of whatever variable you're measuring. So your numerical is distance, independent variable. Dependent variable is the something you're measuring, number of, height of, whatever, counts of. And it'd be nice to put the mean of these 5 here, so equals average. So average is the mean on Excel and also Google Sheets, and it will also fill down, which is nice. I also set my decimal places to 1 decimal place, right, to match the accuracy of measurement here. And then we want the standard deviation. How reliable is our estimate for the mean at this particular distance, right? And you can see that some measurements have got a lot more variability than others, right? So we can't be too confident that this 14.2 really represents the mean at 17.5, so some kind of error bars would be good. And if we type in equals std, standard deviation will give us the right thing. So it'll give us the variability of those 5 data points around the mean, and automatically we've got it. Brilliant. Now I actually want the distance tagged with the mean and standard deviation. I'm going to highlight all of these. I'm going to press Command and I'm going to highlight these. I'm going to press Command C, and now I'm going to analyze this using Data Classroom. Data Classroom, I'm going to import data here, and I'm going to use the first row as column headings. Click, paste. I'm going to call this my bio-quad data. Bio-quad data. Now remember, I was looking for, and I was expecting some kind of quadratic model. Not much happening for low values, quite a lot happening for middle values of the independent variable, and not much at the end. So let's see. We have to tag this with a numerical value, right? So this is a numerical value. The mean we tag as numeric. Standard deviation is numeric. And yeah, that's it pretty much. Now this mean and standard deviation, this mean was actually the mean of variable b, right? So this is variable b, whatever we were measuring as a dependent variable. And pretty much done. Change to graph, switch to graph tab, bring all of your variables to the right so you're able to graph them. And on the x-axis is going to be the distance, and on the y-axis is variable b. And it looks good, right? And you can see that we could put a regression line in, but of course linear is rubbish, it sucks. So we changed linear to quadratic. That's great. But this doesn't represent the whole of our data set really, right? So we're saying that at the distance 15, the variable we measured had a value of 20. Well, that's the mean, but how reliable are each of these data points as a representation for the thing we measured at distance 5? So here we can put on some custom error bars, right? So the custom error bars now, we should be able to choose the source, and the source is the actual standard deviation. Those of you who are measuring things and you wanted to put a fixed value of, let's say, I don't know, 0.1 centimeters or 0.5 or something like that, you can do a fixed value, and here's standard deviation. And we've got this kind of wonderful little options here. Replace dots. I think I'm just going to keep the dots on. Yeah. You can change the appearance. You can change the width of your dots, right? And you can do various things here. But I'm going to change that, leave that now. And then can you see the r-squared value for my quadratic model? This is the coefficient of determination. It's very large. But of course, what we want to know is, sure, that quadratic model is great for the sample of data I chose on that specific day with all those specific abiotic factors happening. But is there a significant relationship between distance and variable b as measured by our quadratic model? And here we just go and click on the magic button, and we're just going to get a p-value for this quadratic model. So we're going to click, we're going to calculate, and it tells you, boom, we have a p-value of 0.84, means actually there's no evidence that there is a relationship. Now, this 0.84 just seems a bit harsh, right? Because when you go back and look at the model, it just looks so amazing that it fits beautifully. But I think the key thing is, can you see the error bars? The error bars are just so huge. You had such a massive range of values at each of these data points, right? That in fact, if you took the lowest value of this, maybe, and the highest value of this blue mean dot we're not that confident of how central it actually is. It could really be the true value of that mean could be anywhere sliding up and down this line. So that's why actually, even though it looks beautiful for the means, it is not a significant relationship.